we have read all the concepts that are required for understanding the voltage current characteristics graph of a diode. You can see the entire graph lies in only two quadrants, first and third quadrant. The graph in the first quadrant is representing the forward bias condition, whereas the graph in the third quadrant represents the diode when it is reverse biased. We know that current can be written as I naught into exponential applied voltage divided by additivity factor into thermal voltage minus 1. We are taking any random value Vs such that if we apply voltage above Vs, we can take the value of additivity factor to be equal to 1, and if we apply voltage smaller than Vs, then we have to take additivity factor to be equal to 2. However, it is not necessary because it also depends upon the semiconductor. For germanium, the value of additivity factor is always equal to 1. Now we mark another point Vin. You can see when the voltage is between 0 and Vin, the current increases very slowly. However, when the voltage exceeds the value of Vin, the current increases very rapidly. The voltage Vin is referred as cut-in voltage. It is the reference voltage such that if we apply forward bias voltage greater than cut-in voltage, then the strength of current is sufficient enough to be of any practical use. Cut-in voltage is also referred as threshold voltage, knee voltage, and offset voltage. One of the most common misconceptions is whether the cut-in voltage and built-in potential are same or different. Obviously, these two parameters are very different. We have a formula for contact potential to be equal to kT by Q into natural logarithm of doping concentration multiplied by acceptor concentration divided by square of intrinsic carrier concentration. However, we are not having any formula for cut-in voltage. It is determined after conducting experiments and plotting the graph. Cut-in voltage is dependent upon temperature as well as the semiconductor material. If we talk about the temperature, then we can say the cut-in voltage decreases with the rate of 2.5 millivolt per degree Celsius. It means that if we increase the temperature of the semiconductor device by 10 degrees Celsius, then the cut-in voltage will decrease by 25 millivolt. For silicon, cut-in voltage varies from 0.6 to 0.8 volt, and the general value is taken to be approximately equal to 0.7 volt. Similarly, for germanium, cut-in voltage varies from 0.1 to 0.3 volt, and the general value is taken to be equal to 0.2 volt. Now we come to reverse bias condition. We mark a point VZK. VZK is representing Zener breakdown voltage. We have studied two breakdown mechanisms, and we already know that Zener breakdown occurs at voltages much lesser than the voltages required for avalanche breakdown. Since the Zener breakdown voltage is lesser than the avalanche breakdown, we represent only the Zener breakdown voltage. And as you can observe from the graph that after the Zener breakdown is reached, there is sharp increase in current. However, the voltage remains approximately the same.